Okay, we can get started. So before we go into our class content, I want to mention two topics. One is related to the Nobel Prize this year, happened to given to chirped pulse amplifier, and we just finished the content of amplifier. So that would be a very interesting thing to talk about. And the other thing is, it's actually left over from last class. I should have mentioned it last time, but somehow I forgot. So last time we talked a lot about this. The superposition of two states. It could be ground state, excited state, or it could be anything, two states that you can differentiate them. And then we say that, well, this is superposition, but when you make an observation, you have to land in one of those states. Okay, can be the wave function collapse into one of them, or you can enter a multi-universe. Okay. And one very interesting experiment I want to mention is the double slit experiment. Okay, light come in, and then go through here. One of the paths, so it's either 1 or 2. Okay, when you have a light coming in, the Young's double slit experiment. When the light come in, it can go through 1 or 2, and then they'll have interference pattern, right? We all know this from classical optics. And then what people have done is that, so the question is, like if you have a lot of light, then you can say this light interfere with themselves. How about if you reduce the incident light into a single photon? Will the photon, like right now because it's only one photon, does the photon has to go through one of the slits, or can it go through both? Like can you do this? And what people find out is that even when you reduce the photon number to like a single photon, let's say per second, and then you accumulate all the photon, then what people see is still the interference pattern. Okay, so what it means is that a single photon really can do this. This is the one thing. And then a more interesting case is when you add a camera here. Well, I think people usually draw an eye here. Okay, when you actually look at this slit. So because the question is, you want to know if the photon goes through both of them or it goes through one of them. Okay. And what happened is, as long as you put a camera here, you can decide whether let's say if you see a photon, then you know it's from 1. Okay. If you don't see a photon, that means it's at 2. Okay. As long as you put a camera here, this interference pattern disappears. Okay. So that's kind of experimental proof that observation can destroy your state. And then it sounds a little bit ridiculous, but yes.
What kind of camera you use?
Oh, I'm not sure.
I mean, it's photon or electron.
So let's see.
So if you use light to observe the electron or photon, then will the light wave or frequency affect the result?
You mean there's some perturbation to it, right? So I think for electron, it's a little bit easier, right? When the electron goes through, let's say this is a single electron going through. The electron goes through, it will create some magnetic field. So it's easier to do. Okay, you can kind of, you say the magnetic field has to couple with something for your instrument to measure, right? Would that affect the electron here? Okay, that's something you can kind of debate on, and then you can actually do experiment to verify it or not verify. So right now, one belief or one argument is that whenever you do observation, okay, you're actually having something interact with the state. But now there's a technique also called I think it's like you can measure a state without actually interacting with it, or you measure something else. So this one is kind of an entirely different subject. But the point here is that the absorption, do affect your result. Okay. Yeah. So this is one interesting thing. Okay. The other thing is the Church-House amplifier. Okay. So the experiment, I think, was done in Michigan, University of Michigan, in 1980s. And then the female scientist who won the Nobel Prize was either a grad student or the postdoc of that group. And then also her advisor also won the Nobel Prize this year. So both of them share like half of the Nobel Prize. And what they do is something called chirped pulse amplifier. Okay. Last class we already derived how to make an amplifier. You just do population inversion, and then if light travels through, because you have more because you have more atom on upper level than lower level, so these photons can trigger some stimulated emission, right? So if you're coming with one photon, you might end up with more photon, right? So this is the amplifier. So why we use Church-House amplifier? So for amplifier, one thing is that it kind of has a maximum, it will have a maximum gain, okay? Because there's only so many, let's say this way, okay? The problem is when people start to try to amplify pulse inside the amplifier, not continuous wave. Continuous wave is like this. Our case is always continuous wave because we are a single frequency, right? We write it down as this. So we have a continuous wave laser. The problem is when you start to amplify pulse. Okay. The pulse from a laser is always periodic. Okay. And what the pulse can do is, suppose the pulse has a width t of tau, and the pulse to pulse separation is t. Then what you can see is that the average power of this pulse times t, the time, unit time, kind of the energy between two of one pulse, will equal to the peak power of a pulse here, peak power, times its duration, right? This is estimate how much energy you have of a pulse, right? And then this is the energy you have within one capital T. So what you can see here is that the peak power of the pulse can be much, much higher than your average pulse, average power. Okay. I think at the time when they do the experiment, at the time it's still femtosecond laser technology. So tau can be somewhere, say, let's take 10 femtosecond. And then I believe they use very large lasers, so this T can be millisecond. Okay. So you can actually gain, let's put it 1 femtosecond just for simplicity. You actually gain you know, 1 billion enhance in your power. Okay. Your average power can be 1 watt, but then your peak power can be 1 gigawatt. Okay. So that's how powerful you are. And the beauty of this is, think about it, if your amplifier can support 1 watt, which is kind of standard right nowadays, you can simply buy a 1 watt amplifier. And you put in a pulse, then you can create something that the peak power goes to gigawatt. So that would be wonderful, right? That would be something wonderful to do. But then the problem came, is that whenever you try to amplify a pulse, the amplifier is always get damaged, right? You have such high power, peak power, it actually damages your gain material. Okay? The electrical field is so intense that your gain material cannot hold anymore. Okay? And so that's why the chirp pulse amplifier came in. What they do is that the idea is very, very simple. So sometimes it's almost surprised that I think that the reason they won Nobel Prize is really because this technology has a wide application, not about how hard it is. Okay, so what they do is very simple. If you put your pulse into, let's say, a long fiber or anything dispersive, what you would see is that the pulse start to spread out, right? And then when it's spread out, the peak power reduces. And then you keep your amplifier safe. And then after it goes through the amplifier, you put in another dispersive material that has exactly the opposite dispersion of the previous material. Then what it would do is that it will compensate the dispersion you see before, and then come back as a pulse. Okay. So this way you kind of save your amplifier, amplify your average power, and then reconstruct a pulse with a very high peak power. Okay. And then this is a technique invented in 1980s and won the Nobel Prize this year. There's some company claim that they can do the commercial product of this. At Caltech, we actually tried to purchase one. I think it still hasn't arrived yet. We purchased it like half a year ago, at least when I was there. It still haven't arrived. So still it's a little bit difficult. Really depends on the tau. Yes.
So what if you spread out that pulse to the point where the
start to overlap?
Are overlapping?
Yeah, that's a very good question.
Is that a constraint where you say you can't?
Yes.
Any more than that?
Yes. So when you start to do that, here it will start to have interference effect, these two pulses. And so that's actually a constraint for, well, the good thing is if you try to disperse a pulse from 1 femtosecond to 1 millisecond, that's kind of almost impossible. So it's like you don't have to worry about it in most of the case. Yeah. But this is something definitely you have to consider when you do the design, especially if your t is large. Or t is small. Let's say if your t is nanosecond, then it's totally possible, right? Nanosecond pulse is kind of common, like in LiDAR. So you can do this transition. Okay, and then what they can do is when they have this really high power, I believe one application is you can go into, because the peak power is so high, what will happen is the peak power is proportional to E squared, right? So your field, electrical field is so strong, then you can have extreme nonlinear effect. Okay? And this nonlinear effect includes, some of them include, let's see. Yeah, some of them include, when we write down nonlinear effect, we say chi2, E squared, chi3. So you generate all this higher order harmonic, right? This one gives you 2 omega. This one gives you 3 omega. And then all the way down. I think with this technique, you're able to do like 20 omega. Okay. So you really can convert. So think about it, that the reason we're trying to do this is because it's not always easy. Well, let's say you can build a laser in telecommunication band, 1550 nanometer. It's very common nowadays. It doesn't mean you can build a laser at X-ray or at soft X-ray, okay? Or, well, not X-ray, the UV wavelength. Because you need to find gain material, you need to find laser cavity. So those things are difficult when you move wavelengths. So what you can do now is that you can start with a near-infrared laser, pulse laser, and then you can end up with the UV short pulse. And that, I believe, is nowadays used to do the laser surgery, okay, in your eye. Okay? Because I think for the eye, it has a typical absorption wavelength, and then you have to target at that wavelength. And then this is one of the application. And the other application is when they do this, amplify the pulse, and then do this very high harmonic, somehow you are able to compress your pulse furthermore. And I think what they can do nowadays is about 10 mmosecond. That's about 100 times better than this. And then again, so one application people are thinking is the chemical reaction. Some of them happen in femtosecond region. So you can send femtosecond lasers and then see how the chemical reaction happens. Okay, if you're in mmosecond, that's about how your atom, move. So possibly you can use this laser to actually see atom-atom interactions. And that one I'm not totally sure if it's true or not. You guys can Google it yourself. And this is still a very young area, and there's a lot to do. Okay. So this is about two things. And nowadays, I think a lot of labs just build their own chirped amplifier, okay, because what you need is just you need some dispersive material, and usually people do grating, okay, optical grating. They use that, and then you have a standard amplifier. You focus the light, you do another grating with different dispersion, and then you're ready to go. Okay. So let's go back to our class, come back to our class. And then last time we said we have Okay, last time we mentioned that we say that we now solve where light go into a 2 energy level system, what its refraction index is, and then when we solve that refraction index, we actually see it can create gain or loss, and you can get EZ0 So when you have N2 larger than N1, you will have a gain. Okay, population inversion gives you a gain. And we can simplify this as we just give it a gain coefficient, G delta N C. Okay? G is our gain. And we know gain, because of this, we can write it down as a G prime, a coefficient related to a material, times delta n. Right, delta n is n2 minus n1, population inversion. Okay, so this is the gain. What you will see when you have light traveling through a gain material, that's the amplifier. Okay. Now the next step is actually we want to use the gain to create a laser. And the basic concept was kind of figured out in 1950s, like the components necessarily, the component you will need to build a laser. So of course you need a gain material. Right, you need a gain material to provide additional photon to a system. And then you actually need a pair of mirror, or what we call is cavity, laser cavity. So what this cavity can do is that if you have your photon let's say you have spontaneously created photon, spontaneous emission, and then this gain material probably can help you to double that number to 2 photons. Okay. And then these 2 photons hit this mirror and then coming back, meet the gain material again. And then become 4 photons. Okay. And then it can keep going and going, bouncing back from the mirror and then taking advantage of the gain material, and you can start from 1 photon to a lot of photons. Okay, and then if the mirror is semi-transmittive, let's say 1% of the light can come out, okay, then you get your laser output. Okay, and probably this material will be covered by Joe Campbell's class, but still I think it's worthwhile for us to spend an hour discussing about this. And to discuss the laser, we want to modify our equation a little bit. The first thing is that we don't want to use E in our equation. Okay, what we want to use is we want to use photon number. Okay. Why we want to use photon number? Because when you have photon number, the thing is naturally there's a conservation law. Okay? If you have 1 more photon in your cavity, that means one of the atom is coming down from the upper level, right? Whenever one atom comes down from the upper level, it generates a photon. So what this can mean is that, just forget all other effects, just considering this emission you will have dz or dt. Right? You have this, if just considering these 2 effects. Okay. So when we write down equations, it will be relatively easy to construct. When we know ds dz, it's relatively easy to construct the dn dz. Okay. And otherwise, if you use E, it's the same thing, but then you have to match a coefficient here. Okay. Now let's give the definition here as, so the energy per unit area, per unit volume for your laser is like this, for your light is like this. And then what you do is you divide it by h bar omega. Okay. Right? The energy divided by the energy of a photon gives you the number of photons. Okay? This is kind of a very common thing to do if your system happen to have some conservation law. Okay? we'll see this also later in the future in other nonlinear effect, when let's say you have 2 photons coming in and then you generate 2 photons at different frequency. So for those equations, typically you also use photon number as your parameter. Okay. And so when we write ds dz, you see it follows the same rule as this one, right? G times S. All right, it's the same thing. Okay, because you have exponential gain. So when you do ds dz, the G coming into the front, and all the coefficient is absorbed on both sides, so it doesn't matter. Okay, so this is your gain, and then the cavity, the laser cavity, will have some loss, right? For example, there's some part of the light is outputting from the mirror, and also the mirror is never perfect. Okay, there'll be some. It's not perfectly smooth. You'll have some Rayleigh scatterings that scatter your photon like outside of the cavity. It's considered as loss. So what we do is that we think about this. Well, let's stop the camera again and then restart it. Okay. So let's think about this system for a moment. Z here is a little bit disturbing, right? Because it's doing back and forth, back and forth. If your Z is from 0 to L, every time you hit the mirror, it actually goes the reverse direction. So Z here is defined as the length the photon travels. It's not the physical position. Let's say if you travel 10 round trip, okay, 10 round trip, so one round trip is 2L times 10 equal your Z. Okay. So this is a way kind of you can make your equation a little bit simpler. To do this definition, Z is the length, travel length, or travel distance. Okay. So whenever it hit a mirror or it actually being scattered, there will be some loss. And then we can give it an average loss, say minus S. Okay. So what this means is that if you travel to the distance when Z equals delta L, okay, if you don't have gain, you just have loss, then what will happen is your S equals E, I think it's minus 1. That's not. Okay. It's kind of your photon will experience a decay, and then this is kind of the typical length. At that moment, you would say that the photon have a very high probability that it's already out of the cavity. Okay. So sometimes people, well, this is actually connected to the full width half maximum. But usually we just write it down as this way. Okay. And we don't care if this number is really 0.5. Okay. Usually that's a half lifetime, but a lot of cases we don't care about this. So this is your equation for the photon inside. And so this Z, although we kind of do a little bit trick, define it as travel distance, write down our equation. The problem is Z is not something you can measure in experiment, right? How can you know how many round trip the light actually traveled? For laser cavity, what we typically know is that you put your laser here, you measure the output, and the output has the power, right? And then you put in a photodetector or power meter, you measure the power over time, right? At this moment, you know the power is this. Next moment, the power is that. And so the t is something you want when you calculate this, because the t is something you measure, okay? And converting from travel distance to t is very simple, because z equals c times t. Speed of light times the time equals the travel distance. So plug that back in here, and you get ds c dt equals gs minus delta L s, right? You put this c to here, c to here, okay? Or we can actually do it this way, 1c. Distance divided by c is time, right? A typical time. So the equation goes to dt cgs minus tau. Okay, tau is our definition of when the photon decays. It's the same idea as the delta L. Okay, here. And here we kind of have set the refraction index to 1 for simplicity. Okay, but the refraction index in most cases is not 1, and then you kind of have to put it back. I think Joe Campbell will cover this content in his lecture. Okay. And from here, then we can already start to see something interesting. So we write out the g delta n minus tau s. Okay. So for ds dt larger than 0, that means your photon inside is increasing. So for that condition, you need this to be larger than 0, right? So whenever your population inversion is large enough, these terms, what it means is that the gain, this is a gain, or effective gain, okay? The gain is larger than your loss, then you have your photon number increasing, right? Makes sense, right? So this is kind of the first laser condition. But this equation is far from complete, because if you just use the equation, what you will see is that then this is larger than 0, then as increase, this term further increase, then the whole thing explode. Okay? If this is true, again, you want 2 Nobel Prize, one in physics, one in Peace Prize. To create infinite energy. So the trick here is that the population inversion is not constant, right? Whenever you emit one photon, one atom has to go down. Although we have pump, right? Although we have pump to move the atom back to the excited state, but still that takes time. So there must be an equation for delta n. All right, delta n is going through this dynamic process. Whenever a photon comes down, whenever a photon is emitted, it comes down to the ground state, and then it goes through the pump, or the pump help it to elevate it back to excited state, and then maintain that population inversion. So there's equation on delta n. Okay. So let's see, delta n. Also, we write down as its change in unit time. So the first thing you will put down here is, because we know every time you emit a photon, then your delta n should reduce by 1, right? So if you just consider the gain effect, you should have this. Right? The rate that you emit photon is the rate that your population inversion change. Right? That's why we define S. the photon number. Actually, my advisor's note, he has a 2 factor here. I'm not sure why, and I can't explain it, so I leave it out. Okay. If you guys, well, I think Joe Campbell would be the best person to ask this question if his note also has a 2. Yes?
So one thing I was reading, you said that in your notes delta n reduces by 1
Mm-hmm.
every time we emit a photon.
Oh, it's reduced by 2, right?
Yeah.
Okay, good. Okay, so that's why we have 2 here. Okay, good. So yeah, n2 reduced by 1, n1 increased by 1, right? So you have 2. Good. So we have 2 here. And then let's see. Okay, so that's the first part. So my note will have to change, and then I will update a new version here. And the second thing is about the pump, right? And the pump is actually following the same idea of this. Okay. First, let's define equilibrium population inversion. That's when you don't have laser. What this means is that the pump will have a rate to I think again this has to have a 2 here. Okay, the pump will have a rate on moving the spontaneous emission, right, will cause your photon coming down from upper level to lower level. That's just natural, A to 1. And also it's proportional to the number of atoms in the upper level, right? If you have nothing in the upper level, then you can't do spontaneous emission. Okay. And then plus the pump. The pump is able to elevate your atom from lower level to upper level. And what this means is that what this can be expressed is that first there's a coefficient. Let's just call it beta. Okay, we don't know exactly what the coefficient is. It really depends on your gain material and how you pump it. But it must be proportional to n1, right? If you don't have any atom in the lower level, then you can't move any atom to the upper level. And also it depends on how strong your pump is, right? If you're using current, in most semiconductors you're using current to move the atom to the upper level, then if your current increased by twice, then your speed of the pump should also increase by twice. And then in equilibrium, this goes to 0. Okay. They should balance. These two effects should balance. And also we have n1 plus n2 equals n. The total number of atom per unit volume is a fixed number. Okay? You can't add more atom into your system. So by these two, okay, you're able to solve n1 and n2, and also delta n, n2, n1. Okay, you're able to solve this. And we define this as delta n. This one. It's not average value. It's simply when you don't have any photon, the gain material itself, or say when you don't have photon, when you don't have mirror, the gain material itself will reach equilibrium. And this equilibrium number, the population inversion number, we label it this way. Okay. And now let's think about it. If your system deviates a little bit from this population inversion, let's say you have more photon in the upper level, then what happens is that your spontaneous emission rate would be faster than the pump rate, right? So more photon would coming back to the ground state. and then slowly it will come back to this level again. Okay? So this effect means that whenever you deviate, right, whenever you deviate from your equilibrium state, you're going to come back. And there's a time constant here, right? How quick you're able to come back depending on your material. Let's say here delta n, let's say it's larger than the equilibrium population inversion, right? Then this is larger than 0. This is a minus sign. So delta n dt smaller than 0, right? And then it starts to coming back, and until it reaches equilibrium. And this number is a number you can probably measure in experiment. So what you do is that you use a pump to move a lot of atom to the upper level, and then suddenly, as long as you can change your current fast enough, you suddenly jump to another level, right? If we draw a map, it's like this. Okay, this is 0. Okay. So at first you prepare your state here, and then suddenly you change your current, or you change something in your pump, and then we know that if you change your pump, then your equilibrium population inversion would change, right? Let's say we reduce the pump, we reduce the current. And you can actually monitor what will happen here, okay? If you're able to measure this, you know the T1 in your system. So this is something probably you can measure, okay? And personally, I've never done this experiment. Maybe there's some clever way to do it, but at least, at least this is one way, okay? Depending on your ability to measure population inversion and also your ability to change your pump, how fast you can change your pump. Okay. So now let's put it here, these two equations. What we have now is ds dt equals to cg prime delta n s minus tau 1 s d n dt equals minus 2 cg prime delta n s, okay, and minus t1. Okay, so this is the equation you have for the laser. I think starting from this part, it's actually almost identical, right? For any laser class, people would use these two equations. I think our class a little bit different side is we actually derive why your gain is proportional to your population inversion. Okay, that's a part. Our class is a little bit different from other class. Let's put S here. Now let's look at this equation. Okay. So first of all, this is a nonlinear equation. S and delta n multiply together. This is called nonlinear equation. Whenever you have a linear equation, means no matter how many parameters you want to solve, if you can write down as, let's see, coefficient beta I, xi, I. if you can write down your equation as this, okay, just a sum of all the parameters, this is a linear equation. It's very easy to solve. And whenever they two are multiplied together, then it's complicated. Okay. In general, this equation, I don't think it has, let's see. I don't think it has analytical solution, or at least it will have more than one analytical solution. Okay, I don't know that. Okay. So typically when you miss something like this, in research, there are two things I would like to suggest. One is to do numerical simulation, right? This one is relatively easy to do numerical simulation. Only two equations, and then the nonlinear term is very simple. And the only thing you have to be very careful about is the dt, okay? In your simulation, what's the minimum delta t you choose for your system to propagate? And this must be much, much smaller than all these terms. Otherwise, your equation, well, your solution will not converge. You're fitting in a lot of, we probably call it numerical noise. Okay. And the other thing that it's actually easier to do is to look for steady state solution. Okay. The reason is the problem is difficult to solve is because it evolved with time, right? We never thought like x plus 2, x plus 1 equals 0. This is not linear, but you can solve it, right? Because it doesn't evolve with time. Okay. So if you put it into steady state and assume because it's steady state, these parameters don't change with time, then although it's nonlinear equation, you're able to solve it. Okay. So in steady state solution, okay, it's 0. It doesn't change with time. And that kind of makes sense if you go into a lab and then turn on the laser. Okay. Whenever the laser is established, the power actually doesn't change much with time. Okay. The reason it changes with time is simply because there's some temperature change in your room that change your gain or change your loss, something like this, but it doesn't change the solution. Okay. And when we have that, then the equation becomes extremely simple to solve. So first equation gives you c g prime delta n minus tau 1 equals 0. Okay. What it says is gain equals loss, and the number of your photon inside is steady, it's stable. You don't change the number of photons. The first equation equal to 0. Okay. And then the second one is this one goes to 0. And I think because I missed a factor of 2 in the note, so if I make any mistake on the blackboard, just point out. Okay. We have these two equations, and then we want to solve delta n and s. Primarily, we want to solve s, right? We want to know the number of photons in our cavity. So first one is simple. You have equals c g prime. Okay, you have this solution. This is your delta n. It's different. It will be different from your equilibrium population inversion, because now you have photon trying to do stimulated emission to a system. Okay, so if you write down this term, actually there would be minus 2b to 1 and 2. Okay, stimulated emission. You have this. So this one would be a little bit smaller. naturally it will be a little bit smaller than this. Think about it in an energy way, right? You emit some photon, of course, your population inversion, the atom on the upper level should be less. If you're able to emit photon and then rise the atom number on the upper level, then it kind of doesn't make sense, right? So this one, okay? And then you plug this in back to here. And we know this one is tau, so minus 2 tau s, okay? This is the first term, minus delta n, plug it in, 1 over Cg tau minus delta n, T1 equals 0. Right, so we have S equals delta n minus Cg tau, and then T1, I think we need to multiply tau here, so maybe I made a mistake again in a note. I think I missed this factor in the note. Okay. Okay. So this is the number of photons in your system. And I'm a little puzzled by why the tau is here. Okay. That means if we have, oh, okay, that makes sense. Okay, yeah, my mistake. That makes sense. So if tau, so let's think about it. Our purpose, let's say when we build a laser, we want to output the maximum amount of power, right? Whenever you build a laser, you want the power to be as high as possible. That just makes sense. So the way to make the power higher, one is, of course, to pump harder, right? Very simple. You just pump harder. And then the other one is that, so if you want your S to be higher, you can, well, let's write it this way. Delta N, right? You want your laser power to improve, then you can increase your pump. And the other thing is you can increase your photon lifetime, right? So when tau is larger, what it means is that this term is smaller. It actually has less loss in your system. So what it means is that if you have a photon, and then it can actually going back and forth many more round trip, and it can induce many more photons. Okay. So when you can't pump any harder, because when you pump harder, you actually create heat, and you create a lot of trouble. And when you can't pump any harder, you make your cavity, laser cavity, better quality, right? You replace it with a better mirror, or kind of, well, sometimes the alignment also matters. So you do this to increase this one. And then the third thing you can do, of course, is you find a better material, right, to reduce your threshold. And the other thing is the T1. You want T1 to be, I think, as small as possible. right? So what T1 means is that is how fast you can recover, right, from non-equilibrium delta n to delta n. Okay, so it also means like actually describe the entire process, how fast this can run. Okay, if you're more efficient to if you're more efficient to move atom from lower energy level to higher energy level, then you have more photon output. So these are the three things that I think this one also is material related. So there are a lot of things you can do here. And I think the laser has already evolved into, I would say, a very special area. And there's a lot of trick when you try to make a laser. What material and then how you combine them to kind of improve your performance. And then that's kind of beyond my expertise. Okay. So, yeah.
Could you explain again why, when we have the laser on, I would expect we want to increase population inversion.
Yeah.
But when we turn it on, it actually decreases?
Yeah, because you generate photon, right?
Yeah.
So then the population inversion decrease.
So this graph is just when I turn the laser on versus.
Oh, you mean this one?
It doesn't feel like pumping or anything.
Oh, this one?
Yeah.
Oh, this one just to explain the T1.
Okay.
Yeah. What is T1? It's like yeah. So it's not the yeah. Maybe we can erase here. Yeah. Yeah.
If you reduce the
I lowered pump power at that instant.
Right.
Yeah, and then how fast? Okay. Yeah, how fast you reduce?
Okay.
Yeah.
But that's not the normal operation.
Yeah. So also one thing that's important here for this equation is it can be negative, right? If a population inversion is not strong enough, it can be negative. So, but you never have negative photon energy, right? So in the experiment, this is called a threshold, right? Only when delta n larger than this, okay, you will have laser operation threshold. So whenever you see a laser publication or whenever you are going to review a paper for laser, this is a typical figure you will see. Here it's either delta n, but delta n is difficult to measure, right? So people put in like pump, what they use to the pump. Let's say they put in current, so you measure milliamp. Or if you do, this is current. If somebody do optical pumping, then this would be the power of their pump. Okay. So what they typically measure is below the threshold, there's kind of nothing or just spontaneous emission. Okay. Sometimes if a spontaneous emission is strong, you will look like something like this. These are all typical. And then whenever you hit the laser threshold and the laser start to build up, then it goes like this, a linear curve, right? Delta n here. Okay. And this is S. So this is a typical laser measurement. Okay? If you don't have a threshold, it's hard to call it a laser, right? Because maybe your light is still coherent, but you're doing it with the different mechanism than this. And I actually happened to review a paper, I think last year, that they say they built a very nice laser, but somehow they didn't include this. And then when I talked to the reviewer, I talked to the editor, I kind of told him that it's a little bit unacceptable. At least you need to explain why you didn't measure this, right? because this is something people have been doing for half a century. And then if you exclude this measurement, you have to explain. You just say you measured that in your previous paper, or you say it's not doable in your measurement. Okay. Now, when the second thing, I think we can go over this. We probably don't have enough time, and but a lot of them are just mathematics. So if we can't finish it in this class, you guys can do it by yourself later. Okay. So one thing is, whenever you do steady-state solution, there's always one thing you need to verify, is whether your solution is stable or not. Right. So you now have S steady state, let's say this solution, and then, wow, which symbol I use? No, fine, okay, right, yeah. Okay. If you have a little bit noise, right? Suppose you have a little bit noise, and let's say this noise is larger than 0. You have more photon than your steady state should. Okay. Then the question is ds dt smaller than 0? If it's smaller than 0, what it means is that if you add a little bit of photon, then the system actually tries to reduce that photon number back to its steady state. So the system is stable. Right? Whenever you add in some noise, if it's a positive direction, you have a negative response. Okay? This one would be stable. Okay? Let's think about it. If it's larger than 0, it's a positive response. That means you just create more photon. And then if you keep doing that, well, actually will keep doing that by himself, then the steady state solution will increase and increase, and then it's not a steady well, it's not a stable solution. It's still a solution, but you can't stay there, right? You can, for any of this non-stable solution, it's very difficult to observe them in the experiment. Okay? So for the laser, for any steady state calculation, you always want to verify this. And then there's a kind of a standard way to do this. Unfortunately, I forgot the name. But it's really about linearize these two equations. Okay. So what you can do is simple. You define your S as steady state solution plus some noise. Okay. And also your population inversion steady state plus some noise. And you always have the noise much smaller than your steady state solution. That's why it's a noise. And we plug that into this equation, and we have d s plus s dt equals to c g prime delta n as s plus prime, okay, minus tau s plus s prime. Okay. So we use this as an example. The same can be applied to the second equation. So first of all, because it's steady state, because this is a steady state solution, this is a number now. Okay, it doesn't change. As long as you don't change your pump, it's a stable solution. This is just a number. So dss dt is 0. Okay. And the second thing is when you expand this, you have CG. You have two steady state solution times together, delta NS SS. And then you have this minus tau SS. Okay. From steady state solution, right, we know this is 0. Right? We plug in the steady state solution. We know these numbers. This one and yes, and this one. We just plug that in. This one goes to 0. Okay. And then we do the other terms. Let's see, CG delta NS S prime plus CG SS delta M prime, and then minus tau SS. Okay. So we reduce our first equation to CG prime delta N prime, sorry, delta NS S prime. Where's this? Then plus CG prime SS delta N prime minus tau SS. Okay. So the first thing you notice, well, we can actually simplify this furthermore, but the first thing you notice is that this equation is linear. Oh, wait, I forgot one term, sorry. Plus CG prime delta N S prime. Okay. So this term. So when we try to further simplify this, we use this condition. Okay. Each of them are very small. So when you multiply them together, they are another order smaller. So this one goes to 0. Okay. And this is actually collinearization of your nonlinear equation. Because what happened is that this is the only nonlinear term in your equation now. All these steady state are numbers, right? So this is the only nonlinear term, and you're letting it go to 0 because it's small. And we can further use this one, this part, and this part, right? When we do lasers, we know CG prime delta N S equals tau 1. Right? We plug that in. CG prime SS. Okay, you get this. It's much, much simpler than the original equation, and then it is steady state. And I would jump ahead, and let's see, so the thing is, because I missed a factor of 2 here, so maybe the equation I write down here is not correct. I'm just guessing where the 2 would be. Okay, should be something like this. There's a factor of 2. Maybe I missed before. And again, this is linear. Linear. Okay. And then how to solve this equation? It's kind of standard. Right? When we have a coupled equation that it has time differential, you do another time differential. Right? So what you can do is you can do to this d squared dt equals to time differential to c delta ns. Let's do that last, minus delta n ns t1 dt delta n. Okay, and then this one minus 2c delta ns ds dt. And this one is this one. Right? You plug that in, you get c g. Okay. Get this. YC has a prime. That doesn't make sense. Okay. I miss a G, right? Okay. You get this. And the next step is to organize all the terms. Okay. Second order differential. We have to extend the class probably for 5 minutes. Apologize for that. And prime plus this term delta n ns t1 yes. And then the other term move that way, and then 2c squared. It looks a little weird, but then I think it's a square here. Right. So I will go very quickly here. Maybe it's not all accurate, but then you get the idea what's happening here. Okay, so equals 0. So this is the equation that you have second derivative, first derivative, and linear term. And it actually looks like this. Right. And what is this equation? This equation is the same as harmonic oscillator. Harmonic oscillator, you have F equals ma. M is d squared dt x. And then you have restore force minus kx. Okay. And then you have, let's say, a drag, right? We mentioned this before, like air drag, a viscous force that holds you back. Okay, and this gives you d squared dt plus km right? These two equations are the same form. They will actually have a very similar solution. So without solving this, you already know what the solution would be, right? Given an initial condition to your oscillator, it will oscillate, but then because of this drag, it will slow down and eventually stop. So if you plot x, you'll see it's like this. Okay. So this is one type of solution when gamma is small. So when the drag is small, it will do this, oscillate and then stop. when the gamma is large, what will happen is it actually wouldn't finish the first cycle. It probably just do this. No, actually not this. Yes, it wouldn't finish the first cycle, and then actually it would do this, just decay. Okay. You can solve this equation by doing x equals x knob e alpha x. Okay. When alpha has an imaginary part, then you do oscillation. When alpha is a real number but it's negative, then you do exponential decay. Right? So there's two situations, but the result is the same. They kind of all go to 0, so that the noise disappear. And for the laser, I think I have a factor of 2 missing there, but you can try to calculate. I believe it's this case. Okay, your laser doesn't even do oscillation. It's very quick. It just get rid of the noise. Okay. So your laser's intensity, if the condition is perfect, nothing changed for the environment, your laser's intensity is very stable. Okay. That's all for the class.